Need a mic or can I stop? Yeah, stand still. That is not easy. Yeah, okay. Dancing around. Okay, thank you very much. Good morning, all. At this very early hour. So my name is Phillipson. I actually work for TNO, and TNO is the Dutch Fraunhofer, you could say, so the Institute of Applied Sciences. And I'm 1 day a week a full professor in Maastricht, at the university, in operations research, and mostly looking into quantum computing and OR. But I will give a bit more of my own background later on. And today I want to discuss with you a bit about the topics in benchmarking that we will see if we are going to do more optimization stuff using other computation paradigms. So what will bring that? Will there be new things that we have to discuss then? Or is it just as we did it always in the past? So my own research is a bit in this area. So on the combination of machine learning, operations research, and quantum computing. And actually from the side of TNO, I look at from the quantum computing part. So if we have a quantum computer, what can we do with it on optimization and machine learning? From Maastricht, well, I'm a professor in optimization, so I take the view from the optimization side and then see, okay, how can we do better optimization using machine learning and quantum computing and other computing paradigms. A little bit about TNO. So TNO is, as Fraunhofer, is a institute for applied sciences. We are not government. We're also not a company. We're something between, but we are independent. And so we were established by law around 1930. We are working in several areas of research, and I'm from the ICT strategy and policy unit. We work on quantum broadly within TNO. So my colleagues at the high-tech industry part are actually building the stuff. So they are working on quantum computers. They engineer them, they build them, but also quantum sensing, quantum sensors they are building. Then in my own unit, we have the algorithm part where I'm working. We have people looking at quantum crypto, quantum communication, and also more the ecosystem development in quantum. And then the colleagues at the defense unit, well, they actually use it all, but then for a defense context. My own department is looking at 3 things, mainly application development. So can we do quantum applications with customers together? In the Netherlands, we also have the Quantum Application Lab, which is a cooperation between the University of Amsterdam, our national computing center, QTech of the TU Delft, and the eScience Center, where we try to combine all our knowledge to help companies in the Netherlands in their first steps on quantum. Then we work on benchmarking and standardization within Europe, also with the Sensenelec organization. And all that we are developing, we try to put in our own code base on GitHub, and part of that are also open source. And today I want to talk a bit about the benchmarking side. So I want to talk about the fair benchmarking of combinatorial optimization having emerging computing paradigms. So of course, working in optimization, in operation research, we have been comparing approaches for ages, of course. And then the question is, did we already do that fairly or not? And the second question is, will that change if we have other computing paradigms? For now, we are using mostly CPUs, and we take one approach and we compare it with another approach also running on a CPU. But already now, but even more in the future, we are going to compare different approaches on different computers. How do we do it? So first, a little bit about the emerging computer paradigms. And to see if you're already awake, I have a small question for you. Which of the following is a real emerging computing paradigm? Is that 1, quantum annealing, 2, emotional-driven cloud CPUs, and 3, binaural solar crypto computing? Well, who think it's 1? Who think it's 2? And who think it's 3? Yeah, for balance, yeah. Well, of course, we know already of 1, and the other 2 are not yet discovered, I would say. But they might come. No, of course not, but we start with 1, of course. And that is just one example of multiple computing paradigms that are existing already. So we came from the CPU. We already work with more dedicated chips like GPU, FPGA, etc. Well, and if you combine those in very large numbers, you go to HPC, high performance computing, supercomputing clusters. Then we have digital annealers, we have neuromorphic computing, and quantum computers. A little bit more background in that. So neuromorphic computers, very interesting stuff. They are actually mimicking the way that a brain works, that a human brain works. So you could say we are also trying that with neural networks. So if you have a computational model that mimics brains, and you are going to combine that with a computer that is also doing the same, well, then something nice could come out. And that's something that also neuromorphic computing is trying. And one of the benefits there is that as the human brain, it is very low power consumption machine, but still also in an experimental phase. Then we have quantum computing. Well, I think you all know about that. So we use there the quantum bits, the qubits, to perform calculations. And well, they can, for specific problems, they can give us up to an exponential speed for specific tasks. And well, optimization might not be one of them, but still we might be able to find better machine-based heuristics, for example, to do approximations of hard optimization problems. Yeah, I don't know what you already know and what you already saw yesterday, but maybe a small overview of quantum computers and the various ways to implement them. So you know, perhaps the gate-based computers that you can just program like we actually do with our conventional computers. So they use the qubits, and we do operations with those qubits. And I think you used Qiskit yesterday. So then actually you build this kind of circuits to do a computation, and you can program them. Then we have the quantum annealers that you cannot actually program, but you can bring them in a certain state, an energy state, and you can embed your program of your problem into those computers. And if they evolve in time, they will find a solution, a low energy solution for your problem that then matches the solution of a optimization problem. And this is only a one-trick machine, but the trick is actually very important for people working on optimization, because it solves, or it approximates optimization problems that are then expressed in a QUBO formulation, so a quadratic unconstrained binary optimization problem. And the last one, the photonic computers, also very interesting, also for optimization, because you can solve some boson sampling problems, and with those you can, for example, solve all kind of dense clique problems, which are also very much found in combinatorial optimization. So we had quantum annealing, but we also have digital annealing, especially they're working a lot on them in Japan. So they are actually inspired by the quantum part, but they use actually a conventional hardware, you could say, so no quantum effects in there. But they also solve the same kind of problems as we do with quantum annealing. Also, the QUBO are the base of the formulation there. They tend also to be, at this point, a bit bigger than what we have in the quantum annealing side. They could also be help in solving those kind of problems. So that was the first part of the emerging computation paradigms. Then a bit on combinatorial optimization, but I think also you know that all. So the idea is to find a best solution from a huge but finite set of possibilities, and that often goes around with grouping, arranging, or selecting items under constraints. Well, I think that's not new for you. Then again, a question to see whether you are all still awake. What makes combinatorial optimization so hard? Well, one, you need at least 3 cups of coffee to start solving them. Some people do, I already hear. It requires juggling physical objects while solving math. The solution space grows as fast as the number of your unread emails, or the number of possible solution grows exponentially with the problem size. So, who needs coffee? Who thinks it's 2, 3, 4? Yeah, of course. Great. And of course, you know all that goes very rapidly. So a very known example is the chessboard, original with grain drops. How is it called? But if you replace it by money, so you have a chessboard, you put 1 cent on the first place in your chessboard, 2 in the next one, 4 in the next one, 8 in the next one, etc. How much money do you find in the last one, the 64th place on your chessboard? Is that 92 million, 92 million, milliard? No, that's not the word. Billion, I think it's in England, in English. Trillion or quadrillion euro? Who think it's A, B, C, D? Yeah, it's the 10 to the 15th euro you find on the last one. So this is an indication that it grows very rapidly when you have this kind of combinatorial explosion. So these problems are at the heart of combinatorial optimization. The solution space grows rapidly, exponential, and actually brute force approaches are in most cases not possible. And they are found almost everywhere in industry. To make a little bit the step to the QUBO, I don't know who already worked with QUBO formulations, also a very small introduction, because it's at the heart of many of the, both the quantum annealing, digital annealing, and also QAOA approaches in quantum. The quadratic unconstrained binary optimization problem is a problem that is characterized by x time q time x, where x is binary, well, we only solve this problem, so no constraints. But of course we can use constraints, but we have to translate them to the objective, and we can do that using some kind of penalty for formulations. So already many problems in practice have been formulated as a QUBO or an Ising problem. You can also say that, and well, the list of problems that has been formulated in some way is growing. And in most cases, the hardest part, especially when using quantum annealing, is to find the right penalty values. Because from a theoretical part, you can derive what is the minimal value of the penalty, such that your optimal solution is also feasible. But when you are embedding that in the quantum annealer, that in most cases will not work that easily, and then you have to tune the right penalty parameter to find a good balance between good solutions and feasibility. So take, for example, a problem from graph theory. We want to find a minimum vertex cover, and that means that we have to select a number of nodes such that all edges are connected of at least one of those selected nodes that we have in the subset. So if we then say, well, xj is 1 if vertex j is in the cover, then we just have to minimize the summation over x. But we have some constraints, and that is that for each edge that we have, with starting point I and ending point j, at least one of them should be 1. So the summation of x, y, and xj for each edge has to be 1 or larger. That means if we want to translate that into a QUBO, we have to find a formulation of that constraint such that it is 0 when it is met, and not 0 or positive when the constraint is not matched. And of course you can think of some formulations to do that. And actually the one that we have to use there is the last one, 1 minus xy minus xj plus the product of xy and xj. And you can see that if you create a truth table, so if they are both 0, then x plus y is also 0, and then the proposed solution gives the value 1, and that's correct because this doesn't meet the constraint. So that means that what we propose as a formula should be bigger than 0, and it is. And for all the other three, the option the constraint is met. So there y plus xj is bigger than 1. And what we also see is then in those cases, the proposed formula is indeed 0. So it does what it requires to do, and we can use this one in the formulation of the QUBO. And then we have to find a penalty value p or lambda or however you call it. And for many classical constraints, there are already known ways to translate that to a penalty value. Okay, I skip this one. And then we go to the part of the benchmarking. So we now know again a little bit about what kind of a computational paradigms do we have, are we expecting, and also that we are looking into the realm of combinatorial optimization. And if we then have a combination of those two, so some solving approach and some computational paradigm that we want to use, how do we actually benchmark this in a fair way? So now the problem, the question is a bit harder than the other until now. But say you have to solve, you have two solvers, solver A, which is fast, but consumes significantly more energy than solver B. What is then the fairest or a fair way to evaluate their performance? Do you then say, well, okay, well, I'm mostly interested in the runtime, because it's all about speed? Or do you say, well, no, in this time we should give more focus on energy consumption? Or do you think, well, we have to consider multiple metrics because it's always some balance in what you want to optimize? Who think it's A? B or C? Yeah, okay, it's some balance. Okay. Well, and of course, we are not the only one who are thinking about this. Also, especially in the quantum computing part already, there is a lot of attention in benchmarking, both on the hardware level, but also in the application level. And well, one of those examples here is the work of McCock, formerly from D-Wave, and she actually suggested 4 principles based on work from the 80s already, I think, from people from computer science. What should we do to avoid misleading the public? And then especially when you are talking about reporting quantum computing performance. Well, the first thing she's saying is, okay, well, we must not claim superior performance without specifying runtimes. So that means you're not going to say, well, approach 1 is better than 2 because the solution it found is much better. Yeah, that can be the case, but without saying something about the runtime, it's not a fair comparison because it's, in most cases, it is a balance between quality and speed. So we have to publish them both. The second one is about, what is actually that runtime? And what she says is, do not report the optimized results without disclosing the tuning time required to achieve them. And so if you have to tune something in your approach, if you have to specify some parameters and you have to find a good set of parameters to run your algorithm, report how much time that takes, because it's a crucial part of your algorithm or approach. Principle 3 is do not extrapolate your results to bigger systems. And especially for quantum computers where we work in very small computers, the early machines. And then if you reach a specific result on a computer with 1,000 qubits, or in the D-Wave case, 5,000 qubits, do not say or do not extrapolate, okay, then if it gets better, we just say, okay, then it will work in this way. So we expect that it will be faster if we have 10,000 qubits or 100,000 qubits. Or at least be careful with that, because we don't know exactly how that explanation will go. We might have other problems then. And the fourth one, but I think that is also very obvious, is try to benchmark on a broad set of instances. So don't take a selective input choice where you just take one or two problems where your solution might be better, but show that it works on a bigger part of the problem space. Or give a good justification if you do not. So why don't you do that? Another approach there is more in the general quantum benchmarking part, based on an article by Langione. They also give some hints about what a good benchmark is. Then the question is good also fair? But they say, well, it has to be useful. It has to say something to the parties that are interested in about what they want to know. It has to be hardware agnostic in that case. And this is, of course, an important one. If we want to compare between hardware types, then it's good that at least the benchmarking approach has hardware agnostic ways of thinking. Then we can do it in a manner about all those quantum computation paradigms or all those computing paradigms together. It has to be scalable, so it should not work just on the computers that we have currently, but also on the computers that we will have in the future. And it should be comprehensive. So it should measure the whole stack or the whole approach that you use as a whole, including all the classical parts that you need to run this. So also here, we hear something about it has to be, so the time that you are reporting has to be the whole process. And then still, of course, we can discuss what the whole process is, but it's not about just the running part. The last example from literature is from Gilbert. He suggested the TACOS framework. And actually, this is a multi-objective framework. So I think you already said that you are interested in that time. That actually tries to combine multiple KPIs, you would say. Solution quality, so how good is your solution? How much time does it take? So the time to solution, and really the wall clock time, so not something about cycles, because computing cycles is hard to compare over the different computing paradigms. It takes into account energy consumption. So how much does it take in the energy part? And what size of the instance set are you covering? And I think this, already meets a lot of the things that we saw before. So it's here also in the time to solution, it says it has to include the entire process. So also in formulation, solution extraction has also had if you use a quantum machine, also the encoding and decoding of the quantum state, the post-processing part, the tuning part, it should all be in there. An And if we then think a bit more on combinatorial optimization, then we have a lot of ways to solve something. And we have the exact solvers, the exact methods in the top of this graph, and we have the approximation methods at the bottom. And then you have also the distinction between approximation algorithms that give some guarantee in this solution that you get, and more the heuristic that do not give a guarantee in your solution quality. And then you have the meta-heuristics that are covering multiple problems, or more the problem-specific heuristics. And of course, if you're going to compare approaches, you also have to make sure that they are comparable. And in this case, make also sure that you say what kind of a approach am I taking? Because the top one are exact, so they will give a good solution, or the best, or actually the optimal, but they are computational expensive. The approximation algorithms give guarantees, are limited in the number of algorithms that exist there, and they are quite costly in design if they are not already existing. The meta-heuristics do not guarantee anything. They're easy in use, but they will be costly, mostly in learning or in parameter tuning. And the problem-specific one, in most cases, they will be good in quality, but they are actually quite costly in design. And you really have to create for a problem a specific heuristic approach. So you can say something about, okay, what is my expectation if I use a specific solution approach? How will they score on, for example, the solution, the time for your design, the time for your preparation, the time for running the actual algorithm? And also here it holds that if you are going to say something about time, computing time, that all those things like design, preparation, running times should be included in what you report. So do not only say something about the running time, but also something about how much does it take to design your algorithm, how much does it take to tune your algorithm. And also, if you run it, and especially if you're going to run it on multiple computing platforms, how do you say something about, did you really use the best available hardware? So what we often see, and I must say I'm also guilty, is that you compare a exact algorithm, say Gurobi-ish, on my own laptop, and I compare that with the D-Wave. Well, my laptop might not be the best hardware available. So am I already then comparing it in a fair way or not? Or should I use the best computer available? Because also the D-Wave uses, well, HPC-ish machines in the preparation phase, for example. Yeah, so is it then a fair comparison if I just compare it with the things I do on my laptop or not? And then, of course, this is nice in theory. However, if you work in practice with all kinds of problems, we have problems around the data quality. So how good is actually the data that you're working on? Is it correct? Is it complete or not? And for example, that also gives you something about the interaction that is needed during solving. So formally, I have a background in telecommunication optimization. So how do you optimize network cables in the ground? And if you then make a planning tool for it, and you think you have all the data, and you go to a planner really in practice, and you say, okay, you have to do this and this and this, there you have to put a cable, etc., etc. And then you come back to you and say, well, okay, but then I need to put my machine over there, and that doesn't fit. So that means that you have an optimal solution, but in practice it's not doable. And that means also that there is interaction needed, that you can say something about, okay, but then I have to adjust my input and run again. So, and that gives you something about how often do you solve it? Do you only solve it once, or is it a repetitive pattern where you adjust a little bit based on the outcome and the discussion with the expert and run again? And that means that only saying something about the quality and the time might not be enough. That, for example, it's also interesting to know something about how the quality of your solution will go through time. That's what those SD diagrams say something. So you start at a certain point, then you're going to run your algorithm, and then, for example, the gray one gives a good solution very quickly. But in the end, the black one is better because it goes further down, and we are minimizing here. So the black one in the end is better. But still, if you want to have an interactive approach, then the gray one might be more useful than the black one. So how to take that into account also. Then a little bit, as the last part of my presentation, about how do we do that in quantum. So one of the examples on the quantum benchmarking part is the Q-score. And the Q-score is an application-oriented benchmark. We have them in two flavors at this moment, a max-cut and a max-click one. And it says something about how good is my solver, quantum solver, for example, in solving a specific max-click or max-cut problem, given the size of the problem. The original one, the original paper shows something like this, and that means that the best quality is a ratio of 1, and that is actually a theoretical optimal bound. And 0 is defined as some heuristic, greedy solver. And then it shows how each of the solving approaches, in this case, it are QAOA solvers, act between those two. So if it would give a optimal solution, the score would be 1. If it's not better than some greedy, very greedy solution, it would be 0. And what they then say, okay, well, we need at least to be 20% better than the heuristic one. That is some ground level of performance. And what you see here is that one of those is actually scoring around 60-70%, and other ones are going through those lower level of performance. But what is the problem in this approach? It doesn't say anything about time. So this is just quality and size of the problem. So what we did was extend that with something like time. And that means that we, for example, give a maximum time of solving. And in this time, and in this example, it was, I think, 60 seconds. So we gave them a budget of 60 seconds and then see, okay, how do it perform then? So here we see, for example, in the left side, that the black one, that is taboo search, is doing quite well, but at some point, with a problem size of around 6,000, then it exceeds the 60-second level, and then then we do not say anything about the score anymore, because then the score actually is 0, because it doesn't find a solution within that time. In this way, we try to introduce an extra level of time into the benchmark. And of course, you can also try to combine that, the maximum time, with not only giving the data to the quality and the problem size, but with saying something about the size of the circles. We will say something about the time needed to find that particular solution. So I think concluding, benchmarking was already important in the past, but it will give some new insights when we are going to use multiple computing paradigms, and it makes it even harder to be all the time fair in how we compare it. And that means that especially if we look into combinatorial optimization, we have to be aware of what kind of algorithms classes are we comparing. Do we take all time that we need for preparing, for tuning in that benchmarking, in that comparison, in a fair way? Do we take, for example, the availability of intermediate results into account or not? So all those things that are points that we have to think about when we are presenting our results, if we find some. Are there any questions?
Yep. Thank you so much for such an insightful and systematic exposition. Yeah, I think we have time for one or two quick questions. Maybe I wanted to ask a question, if possible. So one ivory tower approach, I guess, of comparing different algorithms would be to count elementary operations and think about asymptotic runtimes, right? So I wanted to, so for example, I don't know, how many nodes of the search tree my algorithm explores, or my algorithm explores against the baseline algorithms, and think how does it scale in terms of the problem size. And I wanted to ask, do people do that, especially when we compare classic algorithms to quantum algorithms? And for example, I mean, it's difficult to think about asymptotic runtimes for annealing protocols, for example. So did you see people do that, or?
No, I think that's one of the big problems, because, and also we had the colleagues working on more the classical part of, I forgot the name of that. They're working on, for example, in how much step does it take? So the n square thing. If we have a computation paradigm that does not have computational steps, like neuromorphic, like quantum annealing, they do not take it seriously because they cannot count with it. So then we have to maybe take time, but then also, time is also maybe not straightforward, because do we really use the best way of running it? So there we have the problem of the, is my laptop benchmarkable with a neuromorphic computer or whatever, or do I then have to use a HPC center to make it fair? I don't know, but I think that's one of the big questions that we have. Yeah.
Any other questions? Yes, please. Okay.
In the approaches you proposed about pair profiling, there's many aspects we could understand very quickly. Running times, testing time. There's something that interests me as for industrial application is comprehensiveness. You have any
what is it?
comprehensiveness?
Okay, yeah.
So you talk in the classes that do you have any tips about this? I mean, for the industry, you have to have provide where
Yeah.
what's behind. They need to have it easy to.
No, I agree, especially from practice. Yeah, that's also what I saw in my telecommunication time. That yeah, if you use a solver, Cplex, Kurobi, yeah, then the planners think, okay, well, why should I believe that one? And if I then just take a heuristic that does the steps that they're also doing in their heads, then they believe it because they can check those steps. Yeah, I think that's a very important part. Also, in how we present OR, I would say also. In my own company, I think operational research is not considered state-of-the-art anymore. Everything has to be AI. These days, I say I do not use the word AI, but I use the word explainable AI. Because what we're doing actually is a part of AI, but the way we do it is much more comprehensible or explainable than what AI is doing. But I think that is a very important topic, especially using quantum and quantum machine learning. Yeah, if we do not understand quantum, if we do not understand what the AI is doing, how do we understand the combination of those two? Yeah, it gets harder.
I think we have time one more question. Anita.
Thanks for this very good talk. I have a question about being hardware agnostic. So I understand, or I know from combinatorial optimization, we say the growth behavior is the same no matter on which device. So we can try to be hardware agnostic when we evaluate algorithms, the runtime of algorithms. But on the other hand, we have this area of software, hardware co-design, where you really try to use to design the algorithm and the machine where it is to be run simultaneously, and it shows that you can save a lot of energy or runtime. Maybe not an exponential factor, but still you can save a lot. So the question is this is without you do not consider this, or would you recommend not to consider this, or what is your opinion about this?
No, I think in the end, like the one that I showed, this example, yeah, this try to put it all together, so that we have actually a multi-objective quality score, which tries to include it all together. I think this, in the end, is hardware agnostic, because you can do it. This you can do for all hardware. Yeah? So you do not need something that is, for example, it does not use computing cycles or clocks or whatever, what is specific based for one hardware type. I think this is something that you can do for all hardware. So I would call this already hardware agnostic. You just look at the quality of the solution, the wall clock time, something about the energy consumption. We can do that for all. Yeah. But there's always in multi-objective how to come to one, because we like one single outcome. So we have to combine those four with some weights or something, and